So working again on 12.4, I posted on Google Classroom, there's a handful of questions on here that I forgot were assigned that, normally we would do, but I'm going to cut a lot of these out. The first one, I think, is number 10. We're going to skip 10, and we are going to skip 12, and we're going to skip 13. 12 and 13 both require, 12 requires you to factor, 13 requires you to use the quadratic formula, which, you don't even learn that until Algebra 2. And then if 14, 15, and 16 are even on your homework, I don't want you doing those either. And then everything else, 17, 18, and 19 should all be fair game. So for this, I'm going to do a couple of these. So let's go ahead and just dive into this. I'm going to do 8, 9, for sure. I'll kind of give you a setup for 11, and then we'll go through 17 through 19 as well. All right, so number 8 looks kind of complicated, and these are something I forgot to mention when I lectured. These are great SAT, ACT questions because they look impossible. They look like they didn't give you enough information, but they're pretty simple. The first thing that I see in number 8 is that we do have a diameter. Okay, they did give me a diameter, and then you're going to have to actually go back to 12.2 and recall that when a diameter and a chord are perpendicular, these pieces are congruent and the arcs are also congruent, which is going to actually make these angles, x and y, going to have the same value. Okay, so knowing that this is a diameter, this is 180 degrees, they've given me that this is 120, which means the remaining arc here is 60. Well, the same thing is true up above, and we'll get there in a minute, but let's focus on the bottom half of the circle. So to find x, again, the intersection is occurring outside, and x is this angle. The intersection is occurring outside of the circle, therefore I'm going to subtract. So 1/2 of big arc is 120, minus little arc is 60. That gives me 1/2. When I compute this, this is 60, which half of 60 is 30. So angle x is 30 degrees. We just said these are congruent angles, so y is also 30 degrees. Now, z is going to be 120 because it's the same portion of the 180 as the 120 listed below. But if you didn't know that, you would definitely know this is 60 because these arcs are congruent, and you could just work backwards by saying 1/2 of z minus 60 is equal to 30, and you could solve that to get z that way as well. So know a little bit of your theorems. It makes things super, super easy. Okay? Moving on to number 9. Again, number 9 looks horrific. There's a lot of lines going on, and if you just kind of trust your theorems and know them, then you should be in good shape. So the first thing I'm going to do with number 9 is, again, understanding when you have inscribed angles, they give you the arc measurement also. So this angle that is 34 degrees is creating this arc right here. If I double that, that'll give me the arc measurement. Okay, therefore the arc measurement in this case is 68 degrees. Why does that help me? Well, because that arc paired with this little arc is needed to find x. Okay? Well, if I look at the angle that is 18 degrees and I trace it, that's creating this little arc here. And that angle is 18, it's an inscribed angle, therefore if I double 18, I get that pink arc that I just created, which when you double 18 is 36. So to find x, it's 1/2 of the big arc, now is 68, minus, because your angles occurring or intersecting outside, 36 is equal to the value of x. When I do that, you can type that in your calculator, x is 16. Okay? Now, the hard part left is y. So let's erase some of this stuff, give ourselves some more room to work here. I think everybody would agree with me that when I say that we have a triangle inside, all right, and then you have angle y, which is an extended or exterior angle of the triangle. Now, there's two ways to do this. There's a fast way and a longer way. I'm going to do the fast way first. Think back to chapter 6. we learned that when you have a triangle and it has an exterior angle, the exterior angle is equal to the sum of the two remote interior angles. So if you just take 34 and 18 and add them up, you get the value of y is 52. Okay, that's a theorem we learned a long, long time ago. If you don't like that, that's fine. You still have to recognize that this is a triangle. You can add 34 and 18 and subtract that from 180. When you do that, that tells you that this angle right here is 128 degrees. Because I added 34 and 18, it was 52. I subtracted that from 180 and got 128. Well, now the 128 and angle y are a linear pair. So if you take your 180 and subtract from it your 128, you get 52 degrees. Okay? So that's the longer way to do that. I said we were going to skip number 10. Take a quick look at 11. I'm not going to solve this per se, but this is a direct application of the last theorem in your notes. It is, I think, would be second. No, I'm sorry, this is the third of those three cases that they gave you in that theorem, which simply says you take your two parts of your chord, 2 plus 9, you add them together, and you multiply by whatever value is outside of the circle, and that is equal to, and in this case, this is simply just going to be z squared. Okay, so you can solve that one, no problem there. Moving on to, because we're skipping the next three questions, I guess. So down here to number 7. For all of these, or at least 17 and 19 rather, you're going to have to find pieces and then go back and add them in later. So what I mean by that is if we take a look at number 17, I think the very clear thing that we see is we have a right triangle. Okay? And the question is asking me to find the length of the diameter of the circle. So I need to know this entire line, that whole diameter. I'm going to start by figuring out what this length is, because I can use the Pythagorean theorem to find that length from red dot to red dot and then continue to work. So if I use Pythagorean's theorem, the 10 is my hypotenuse, so 10 squared is equal to 6 squared plus x squared. I'm going to save myself some work here. X is going to end up being 8. So from here to here is 8. Okay? Now, again, the same theorem we had to recall in number 8 from chapter 12.2, you have to recall here again. If a diameter and a chord are perpendicular, the diameter is also bisecting the chord. So if one part of the chord is 6, that means that piece is also 6. Now, going back to your theorem from 12.4, this is the first case of your last theorem, right, where we have the intersection of a couple chords inside of a circle. Let's call this piece the unknown x. So 8x is equal to 6 times 6. So multiply this piece and this piece equals this piece times this piece. Okay? When I do that, I get 8x equals 36 and x equals 4.5. But you're like, wait a minute. The answer says 12.5. Correct. Reason being, I only found that piece is 4.5. They want the length of the entire diameter, so I have to add the 8 plus 4.5 to get my 12.5. All right? Number 18, I'm not going to do this one entirely, but I will tell you if you call the diameter x, this looks identical to, in fact, identical to number 11. Okay, so call your diameter x. It looks just like number 11. It also is case 3 in that last theorem in your notes for 12.4. And then number 19, again, is going to be similar kind of to number 17. In this case, again, we're looking for the length of the diameter, but the diameter is perpendicular to this chord. Therefore, if this piece is 4, that piece must also be 4. So, I can use my case 1 in that theorem. I'm going to call this x for the time being. So 3 times x is equal to 4 times 4. When I, cross multiply, but when I divide both sides here, x equals 5.3. 5.3. Again, that's only the length from here to the edge of the circle. So I need to find the whole diameter, so I take my newly found 5.3 and I add it to 3 and get 8.3. All right, any other questions, drop me an email.